Welcome back to this lecture series on pulse width modulation for power electronic converters. So, let us take a quick look at what are the various modules that we have covered so far in this course now. So, as you are aware, initially we started with an overview of power electronic converters. This was probably one of the longest modules covered till now. We looked at various kinds of power electronic converters, started from switches and then we went on to DC-DC converters, buck, boost, etc., and we looked at voltage source and current source converters, multi-level converters, etc. Then we had a particular focus on 3-phase voltage source converter, and we looked at applications of voltage source converters. And applications of voltage source converters would be like the most important application that we are concerned about here is motor drive, that is an induction motor drive. Other than an induction motor drive, there are other things that you are going to look at. For example, we are looking at active front end converters, and you are looking at power quality equipment such as static compensator, which you can use for compensating supplying reactive power to the system. And further, you also use voltage source converters when you want to clean up the harmonics drawn by certain loads, that is harmonic filtering, active filters as they are called. So, these are the various applications. We had a quick review on these various applications, and you may remember that each one of these applications could actually be a course by itself, and we had a very quick review on this now. And once we had this, the role of a voltage source converter, we looked at pulse width modulation for voltage source converter, and we first looked at the purpose of pulse width modulation. And if you look at it, the voltage source converter, there are three things. One is the DC side voltage, then the AC side voltage, and the modulation. So, the purpose of pulse width modulation is to make sure that on the AC side you get the desired fundamental voltage, but in addition to the fundamental voltage you also get some harmonics. So, the trouble is you want to avoid those harmonics. So, the purpose of pulse width modulation, as we saw, was to control the fundamental voltage and to reduce the harmonics and their ill effects. So, these are the main purposes of a pulse width modulation, and then with this we went into low switching frequency pulse width modulation, where you barely have one or two switching angles, very few switching angles in every quarter cycle. I mean, the inverter switching frequency is very low, is just a few times that of the fundamental modulation frequency, like 5 times or 7 times. If you are taking a modulation frequency 50 hertz, we could consider just a switching frequency of 250, 350 hertz, etc. So, I talked about the practical relevance of this and why it is relevant from an academic point of view, etc. earlier. And this is probably where the last two, this is where we came to like these are what you would call as now very important PWM methods, and the triangle comparison method is what is probably most relevant from a practical point of view. If somebody is familiar with many of these material, then this is probably one where one would particularly focus on. And in many of these practical converters, we do have this triangle comparison based PWM. The best known of this category is the sine triangle PWM, where you use sinusoidal modulation signals and compare them with the triangular carrier, and you produce PWM signals. And to the sine you can add some third harmonic, or you can add many other triple frequency components, common mode components. This is what we discussed in the previous module now. So, today we are going to start up with a new module, which is again about PWM generation. So, the earlier module was about generating PWM for a 3-phase voltage source converter, that is following what is called as a triangle comparison approach. Now, once again we are talking of generating PWM for the voltage source converter, but what happens is we are going to use a different approach, and what is called space vector approach. So, we are going to deal with space vector based PWM in this module now. So, what is the space vector based PWM? So, these are the various things that we will be covering as part of this module. So, first we would look at the concept of space vector. That is what we would primarily be doing today. So, once what is a space vector, we understand the term space and we understand the term vector individually. So, what we mean by the space vector is something we need to look at. And then we would look at what is called a space vector transformation, that is actually 3-phase quantities can be transformed into 2-phase vectors, and that is what you call a space vector transformation. We would look at this, and from then on we would go into conventional space vector PWM method, which is the most popular PWM method using this space vector approach. So, that is conventional space vector PWM, I would say, is as popular as sine triangle PWM, I mean if not more popular, and in fact its benefit is compared to sine triangle PWM, it can give a higher amount of AC side voltage for the same DC bus voltage. I mean, whatever advantage we got with third harmonic injection, a similar advantage you can get with this conventional space vector PWM also. So, we will be discussing this conventional space vector PWM now. So, this is what I would call as the most important method using the space vector approach now. And there are alternative space vector based approaches. This bus clamping PWM, you recollect that the discontinuous PWM or bus clamping PWM, which we discussed in the earlier module, triangle comparison methods, we will now discuss in this module also. How to produce this bus clamping PWM, not by comparing triangular carriers and a modulating signal, but from the space vector approach is what we would also be looking at from this now. And then these two methods, triangle comparison and space vector, would look a little different from each other, but actually they have lots of similarities. So, we would look at the equivalence of triangle comparison and space vector approaches to PWM, and most of the literature stops here. There are very if you read through good part of the literature, you would get a feeling that both these approaches are pretty equivalent, but what we would like to stress in this course is space vector approach is a little more general than triangle comparison approach. That is, whatever can be done using triangle comparison approach, whatever PWM waveforms can be generated using triangle comparison approach can also be generated using space vector approach. On the other hand, everything that is possible using space vector approach is not necessarily possible using triangle comparison approach. I would call space vector approach as more general than triangle comparison approach, and one category of space vector based PWM is this advanced bus clamping PWM. These PWM signals can only be produced from the space vector approach and they cannot be produced from the triangle comparison method, is what I am going to talk about towards the end of this module now. So, that is just to give you an overview of what you would expect in this module, which we are hoping to cover in 4 lectures. I am just getting started with today's lecture, the beginning of this module, that is the concept of space vector. What do you mean by a space vector now? Let us start with an example. This revolving MMF, this is about an example of a space vector approach of what is a space vector. So, this revolving MMF in 3-phase machines, that is what I would like you to consider. Most of you should be familiar with 3-phase machines, and even in this course we have been dealing with 3-phase machines on and off. Now, you consider a 3-phase machine like a 3-phase induction motor or a 3-phase synchronous machine. So, what you have is you have a 3-phase winding sitting on the stator, and what you do to the 3-phase winding, you apply 3-phase sinusoidal voltages usually. And when you apply 3-phase sinusoidal voltages onto this 3-phase winding, it produces a revolving MMF. There is a magnetomotive force, there is a field, there is a magnetic field produced, and that magnetic field revolves the air gap. This is what happens now. And this revolving MMF is what, where does it revolve? It revolves in space. So, in some part of the air gap at some angle, you might find the peak, the magnetic field, the flux density might be at its peak now. It will gradually move around the space. So, this is a revolving MMF. So, that is it's actually a vector which really moves in space, and so you can call that as an example of what is a space vector now. So, let us get a little more into this, what we mean by a revolving magnetic field. So, a step towards understanding revolving magnetic field is a pulsating magnetic field. A revolving magnetic field is produced by 3-phase winding, a pulsating magnetic field is produced by a single phase winding. So, first let us take our time and slightly review this pulsating magnetic field produced by single phase winding, and from then on build that understanding to a 3-phase winding. This many of you would have done a course on machines, but it would be good certainly to review this here now. So, now you have this rotor, it is clear. So, it is marked rotor, and this innermost circle stands for the rotor. Then this small ring that you have is the air gap, and what you have here is the stator, and it is also written as stator here. And on the inner periphery of the stator, you have a few conductors here and you have a few conductors there. They are placed kind of diametrically opposite to one another, which is the case in most machines. Sometimes the return path is not exactly 180 degree away. So, what are called as short pitch coils, and usually use full pitch coils. So, you can say that there are conductors going here and conductors going here. For the conductor here, the return path is here, for the conductor here, the return path is here, for the conductor here, the return path is here. That is how we assume. So, anyway, those details are not very important for this purpose now. Let us say you have a coil. What does this coil do? It produces a magnetic field. What is the direction of the magnetic field is an important question now. Well, that depends on the direction of current flowing. So, let us consider some direction of current flowing. Okay. What would be the direction? Let us say the current is dot, and the current here is cross. I hope most of you would be familiar with this dot and cross. Dot basically means current is flowing out of this sheet. It is like an arrow coming out of this, you just see a point. So, it is like current coming out here. and cross is like arrow penetrating into the sheet. So, arrow means current is flowing into this now. So, if you do this, what is going to be the direction of this? Well, you can hold on to your right hand and you can look at this, and now for current flowing out to the top, this is going to be the direction of magnetic field, and this is what you would call as the axis of this magnet. What is going to happen is this is going to produce magnetic field which really goes around these things, and this is what is really the axis of this magnet. And when the current is constant, this magnetic field is a constant magnetic field. When this current varies with time, certainly the magnetic field also varies with time, but the axis is unchanged. This is the axis of this magnetic field. So, if the current alternates, then the magnetic field also alternates. Sometimes it is in this direction, sometimes it is in the other direction, and the amplitude goes on changing, its magnitude goes on changing. So, you might get a pulsating magnetic field. So, let us get a little clearer about the pulsating magnetic field. Let us do that mathematically. So, what are we going to do that to deal with it mathematically? So, let us say you have this MMF. So, what is this F? F stands for MMF. R stands for the winding, it is R phase winding. We are just considering a single phase, and just let us call that simply R. And 1, basically whatever MMF is produced by a winding, let us say like what you have here, it would be it would be some alternating waveform. It need not be sinusoidal, it will not be sinusoidal. To make it closer to a sinusoid is why you do a few things, you design this, you distribute the windings and all that, but but still it is not sinusoidal. But most of the machine analysis you would ignore the spatial harmonic components and you will deal with fundamental component there now. So, when I say this 1, the subscript 1 refers to the fundamental part of the MMF. So, the spatial harmonics of this MMF are ignored, and this what you have is FR1, that is the current passing through this R phase winding produces some MMF. So, the fundamental part of that MMF is what is taken as FR1 now. So, what is that? That MMF should obviously be proportional to the current that is flowing through that, right, IR. So, it is IR there, and K is some constant of proportionality, and now this theta is the angle. For example, if you consider here, let me say you consider like this angle you can call as theta AE. Theta is because it is an angle, A to say that it is air gap, and E is the electrical angle. I am talking of the electrical angle here. I am just considering it as a 2-pole machine for simplicity. So, you just take it as theta AE. This is what you have now. So, if the magnetic field is highest here, as you go around that, the strength of the magnetic field will go on reducing, and the magnetic field will be 0 here, and if you go here it will be negative peak here, and then strength will reduce and it will be 0, and then it will be back to positive. So, you will get a distribution which is alternative, and which is actually you can presume it to be sinusoidal distribution now, and therefore, what you will have is this is what you get here, that is cos theta AE would be the MMF there at that angle theta AE now. So, I am just not getting into the details of K, that would, for one thing it would involve the winding distribution factors etc. So, I am not getting into that. So, that is a constant K, let us simply leave it at that. FR1 is K IR cos theta AE. Now, what is that IR? That is not going to be a constant current, you are going to be injecting an alternating current, Im cos omega ET is there. Omega ET is the fundamental angular frequency. If you are talking of fundamental frequency 20 or 50 hertz, this is 2 pi into 50, 100 pi, that is radians per second, that is omega E. So, you have, and Im is the amplitude of that cosinusoidal component. So, you have IR is equal to Im cos omega ET. Therefore, you put one into the other, you have FR1 is equal to K Im cos omega ET cos theta AE. Therefore, you find that this MMF, the spatial MMF, it is a function of spatial angle theta E, and it is also a function of time t. So, it is a function of both space and time. Now, it is a product of two cosines. You can always write it as sum of two cosines like this. So, it is f max by 2. This K Im, let me give a term called f max for that. Let me just call that f max for convenience, and this f max by 2, I can say that it is cos theta AE minus omega ET, which is basically the difference between these two arguments, plus cos of theta AE plus omega ET, which is the sum of these two. That is what you have now. So, I can write this as this FR1 as two different components, theta AE minus omega ET, theta AE plus omega ET. So, now what really happens is this itself is one component, which rotates, this is another component which rotates now. One rotates in the positive direction or the anti-clockwise direction, the other one rotates in the negative direction or the clockwise direction. So, you can write this FR1 as some FR plus and FR minus. The clockwise component you can write it as FR plus and FR minus. Thus, you can resolve a pulsating magnetic field into two, a revolving magnetic fields, as many of you might be aware. In fact, this is what is actually used in an single phase induction motor also. You produce two magnetic fields and this won't be able to start. What you will do is you will do some trick, you will slightly weaken one magnetic field and strengthen the other one. So, strengthen one relative to the other and you will get the machine running. So, that is what you do in a single phase motor, as many might be aware. So, most of you should be aware of the fact that the pulsating magnetic field can be split into two revolving magnetic fields, one rotating clockwise and the other rotating anti-clockwise. So, this is the math just behind what you can, behind this statement now, right. So, now instead of one winding, what you have is you have three windings. So, you can say that this is the old R phase winding we are talking about, these are the corresponding return conductors now. Then about the Y. So, for Y what I have done, I have used green color here. So, this is the Y phase belt and the corresponding belt is Y here. Then the B phase I have used blue color here and this is one, that is one now. And if you look at the various axes, what you can find is the R phase axis is like this. So, you have these windings and you have these windings, the R phase axis is like this, as we saw earlier. This is R phase axis. How about Y phase axis? You have these windings and this phase belt here, and Y phase is, it goes like that. This would be your Y phase axis in a machine. And what is the axis of the B phase winding? You have here and here, this would be the B phase axis. These are the axes of the three windings of this machine now. So, let us look at what happens when they are excited. These three phases, now I am just the same three phase windings, I am putting them in a different form. I am just indicating the three axes here, calling them R, Y, B, as I said before. And we pass certain current through this R phase winding. What is that current? IR is equal to Im cos omega et. It is a sinusoidal current. I am taking that the value of sine, that is equal to 0 at time t equal to 0. So, I am writing this as a cosine function here. IR is equal to Im cos omega et. If that is the current, then the Y phase current is Im cos omega et minus 120, and the current through the B phase is Im cos omega et plus 120 degree, right. So, this is what we have, and from this we move on. What we are doing is three phase windings, we are we are passing three phase sinusoidal currents through the three windings now. So, this produces a revolving magnetic field. How? First we had this earlier case, FR1 is KIR cos theta AE, as we had said before. Now, if you had considered the Y phase axis, Y phase MMF would also be the MMF produced by the Y phase winding will also be some proportional to the Y phase current. So, it is KIY, and cosine of, now we are looking at the MMF at angle theta AE, but the Y phase itself is at an angle 120 degrees from the R phase, and this is theta AE measured from the R phase axis. So, this is theta AE minus 120, cosine of that is what would be the component along Y phase axis. So, FY1 will be proportional to cos of theta AE minus 120. Then you have the MMF at that angle produced by the B phase winding. So, the current flowing through the B phase winding is IB. So, this is FB1 is equal to K IB cos of theta AE minus 240. That is because the B phase winding is 240 degrees away from the R phase winding, and hence you have this now. And what are our IR, IY and IB? Im cos omega et, Im cos omega et minus 120, Im cos omega et plus 120, or this is also minus 240. So, these are the three phase currents that you have now. So, plug in IR, IY, IB into the previous thing, you get a similar expression as we found earlier. Each of them produce a pulsating torque, pulsating magnetic field, as we discussed before. FR1 is F max cos theta AE cos omega et is. So, F max is now this K into Im, that is what is taken in that way. Similarly, Fy1 would be F max cos of theta AE minus 120, and Iy is substituted by Iy is proportional to cos omega et minus 120. So, you get this cos omega et minus 120, and if you take Fb1, that is F max times cos of theta AE minus 240 multiplied by cos of omega et minus 240. You see the difference between theta AE and omega et, and you again see the difference between this argument and this argument. The difference between theta AE minus 120 and omega AT minus 120 is the same, theta AE minus omega AT as before. Similarly, theta AE minus 240 omega AT minus 240 also the difference is still the same. So, let us write down the equations further. What you can say is FR1, FY1, FB1. They can also be written as F max by 2 multiplied by something, the sum of two cosine terms. The first term is cos of theta AE minus omega ET, that is the case for all the three phases. The second term would be cos of theta AE plus omega ET, that is basically the sum of these two, it is basically the sum of these two terms and the sum of these two theta AE plus omega ET. In the next cases, it is theta AE plus omega ET minus 240, which is plus 120, and in the third case the sum of the two is theta AE plus omega ET plus 120. So, this would be plus 240 here. So, this is what is here now. So, the R phase, Y phase, B phase, all the three of them produce pulsating magnetic fields, and each pulsating magnetic field can be split into one component revolving in the anti-clockwise direction and another component revolving in the clockwise direction now. So, the ones revolving in the anti-clockwise directions are adding up. Now, the ones revolving in the anti-clockwise direction, you add these three, they will sum up to 0. So, here you can call this as FR plus, Fy plus and Fb plus, they add up. They add up to what? 3 into F max by 2 cos of theta AE minus omega AT. On the other hand, these three, this is some cos of x, this is x plus, then there is another 120 degree added here, there is another 240 degree added. So, these three cosines add up to 0, Fr minus plus Fy minus plus Fb minus would add up to 0. Hence, it essentially becomes equal to it should have been 3 times Fr plus. So, just you make a change into that. So, this would be simply be 3 times Fr plus is what would be your sum of that, and that is nothing but FAG1 is 3 by F max by 2 cos of theta AE minus omega AT, and now this you can see is a revolving magnetic field. So, thus you get a revolving magnetic field produced by 3 phase windings excited with 3 phase sinusoidal currents. So, this is a revolving magnetic field, and now if you want more on this revolving magnetic field, you can actually take any book on electric machines. So, one of the references I would suggest is A. E. Fitzgerald, Kingsley and Uman's Electric Machinery by Tata McGraw-Hill 2003. Well, there are also different editions of this book available. I mean, there are also older editions of this, and there are several books in the subject of electric machinery. So, you can actually take any textbook on electric machines, and that would be able to give you a very good picture on the revolving MMF to greater extents, and particularly the design of windings and many things. If you want, you can actually look at those books there now. Our main interest in seeing this is revolving MMF is one example of a space vector. So, we are just first trying to understand that is what we are trying to do now. The next thing is, from this we have to go into gradually understanding a space vector in a more general sense, and coming up with what really would be space vector transformation. Now, let us just say one thing. Now, you have 3 phase windings, and what does a 3 phase winding do? It essentially produces some MMF which rotates like this. This is what it does. This is done by 3 phase winding. Now, the question is, can it not be done by 2 phase windings as shown here? That is, I can also have a 2 phase winding, that is one I can call as alpha, the other one I can call as beta, and this alpha and beta are 90 degrees away from one another. They are separated in space by 90 degrees, and I can also excite them with currents which are shifted 90 degrees in time, and by doing this I might be able to produce the same kind of revolving MMF using this 2 phase winding now. So, for a 3 phase winding, you could consider an equivalent 2 phase winding which really can do this job of producing a revolving MMF now. Let us go a little further now. I have shown the 3 phase axis R, Y, B simply as lines here, and this is the revolving MMF that I pointed out earlier. So, this is a revolving MMF, a corresponding revolving MMF can be produced here. Let us write down the equations. If you really want to do that, what should you be doing? The 2 MMFs are supposed to be equal. What are the 2 MMFs? One MMF is produced by this current I alpha, excuse me. So, there is alpha winding, and through this there is some current I alpha flowing, and through the beta winding through which some I beta is flowing. So, this n times I alpha should produce a component along the alpha direction, and this I beta, that n times I beta is the component along the beta direction now. So, n times I alpha should be equal to what? Now, the R phase is the one that produces the MMF entirely along alpha axis. So, it is n times I R, and a component of the MMF produced by Y phase is along the alpha axis, that is n I y cos 120. Again another component of the MMF produced by the B phase winding is along the R phase axis or the alpha axis. So, this is n I b times cos 240. So, you need to satisfy one condition, n I alpha equals n I r plus n I y cos 120 plus n I b cos 240. This is one of the conditions that you really have now, right. This is one condition. And how about the current n I beta? So, n I beta is the MMF along the beta direction. Now, R phase winding does not produce any MMF along the beta axis, it produces it's aligned along the alpha axis, therefore, it does not produce along that. So, what is the MMF produced by the this 3 phase winding along the beta axis? It is n I y cos of there is something this should actually be n I y times you have cos of 30 degrees. Let me just change that here. So, if you look at it, it is going to be cos of 30 degrees. Sorry, there is a mistake here. So, this is cos of 30 degrees now. And what is this? Again, this is n I b, and that is going to be this beta axis is 150 degrees away from here, right. So, this is 30 degrees, and you have another 120 degrees. So, this is going to be 150 degrees. So, this is going to be cos of 150 degrees. Now, cos 30 degree is root 3 by 2, cos 150 degree is minus root 3 by 2, and this is actually it is a plus sign here, you can say plus n I b cos 150. So, this is what you really have. So, you can produce whatever is the revolving MMF produced by a 3 phase winding R Y B can also be produced by a 2 phase winding alpha and beta whose axes are separated by 90 degrees, provided your I alpha and I beta satisfy the two equations given here. So, that is what I am writing down in the next slide. I alpha should be equal to I r times cos 120 plus I b times cos 240, and this should be I r minus I y by 2 minus I b by 2, and further your I y plus I b is equal to minus I r, because your I r plus I y plus I b is 0. Therefore, I y plus I b is minus I r. Therefore, you get this as 3 by 2 times I r. So, this is what you have 3 by 2 times I r. So, I r plus I y plus I b. Then how about your I beta? It is the same mistake that is carried over here also. So, this is going to be cos 30 degree, and you can say plus, and this you can call this as cos 150 degree, and this will be root 3 by 2 times I y minus I b. So, this you can call as, so you can the MMFs are equal, that is the MMF produced by a 3 phase winding excited by currents I r, I y, I b is equal to the MMF produced by 2 phase winding alpha and beta carrying currents I alpha and I beta if I alpha is equal to 3 by 2 times I r and I beta is equal to root 3 by 2 times I y minus I b, and this is what is space vector transformation of 3 phase currents. That is what is reproduced here. I alpha is equal to 3 by 2 times I r and I beta is equal to root 3 by 2 times I y minus I b. So, we can just simply write this in a matrix form. You can write I alpha I beta, and this is 3 by 2 0 0 0 on the first 0 and 0 on the first axis, 0 root 3 by 2 and minus root 3 by 2. You multiply by this by another matrix I r, I y, I b. So, I alpha is 3 by 2 times I r, I beta is equal to root 3 by 2 I y minus root 3 by 2 I b. So, this is space vector transformation of 3 phase currents. I have just given this in a matrix form here, just for convenience. Sometimes you might find that convenient now. So, what is applicable for 3 phase currents? Now, we are looking at 3 phase voltages. So, you can also extend this idea to 3 phase voltage, where also you have the same condition V r n plus V o n plus V b n is equal to 0 if you are considering a balanced star connected load. That is, I am considering a star connected load. So, n is the load point neutral. Okay. So, now V r n plus V o n plus V b n is equal to 0. Under this condition, what you can say is you go by your same thing as V alpha is equal to V r n plus V y n cos 120 plus V b n cos 240, and that goes to add up to root 3 by 2 V n. The same mistake is perpetuated here also. So, you can probably call this as cos 30, and this is plus you can write, and you can write this as cos of 150 degrees, and you can see that this is going to be root 3 by 2 times Vyn minus Vbn. So, it is the same transformation that you are getting here also. So, you know that, so this is the transformation for 3 phase voltages into, it is very similar to that. V alpha is 3 by 2 Vrn and V beta is equal to root 3 by 2 times Vyn minus Vbn. So, this is the 3 phase transformation of a space vector transformation of 3 phase voltages. So, 3 phase voltage is converted into an equivalent 2 phase voltage. So, what you see here is you first have a situation, let us say IR plus IY plus IB is equal to 0. This is from KCL. So, this is a 3 wire load and the sum of the 3 phase currents is 0. Similarly, you can consider when the load neutral is not connected, it is a 3 phase, it is a 3 wire load and you have balance indeed, you have Vrn plus Vn plus Vbn is equal to 0. This is the kind of 3 phase voltage that you have now. So, both these equations if you see, they are of the form x plus y plus z is equal to 0 in the Cartesian coordinate system. So, what does x plus y plus z is equal to 0 represent in the Cartesian coordinate system? It is the equation of a plane. So, it is a 3 phase quantity, but you see that the 3 phase quantities are not 3 independent quantities because they are equated, you know, they have a relationship. So, similarly here Vrn plus Vn plus Vbn, this 3 phase quantity does not mean the 3 phase, they are 3 independent quantities, they are actually, they represent a plane. And how many dimensions does a plane have? Only 2 dimensions. So, a 2 dimensional space can be spanned by simply 2 orthogonal vectors. So, a 3 phase quantity like this can be represented by just a 2 phase quantity I alpha and I beta. Similarly, a 3 phase quantity such as this can be represented by 2 phase quantities, namely V alpha and V beta. That is the moral of this. The 3 phase quantities sum up to 0 and they can be represented only, by only 2 independent quantities now. So, for further reference you can look at this book by Holtz and Lippo on pulse width modulation for power converters, principles and practices. You can particularly look at chapter 1 of this book, where there is a section on the concept of space vector, where this is discussed further, right. So, this is our idea of a space vector. So, now we have come up with what is a space vector and how it is space vector transformation, and we have got transformations for 3 phase voltages and 3 phase currents now. So, now what we are going to look at is we are going to look at the specific case of a voltage source inverter. So, you have voltage source inverter, it has a DC voltage VDC, it produces some AC side voltage. So, RYB, this AC side terminals, these voltages can be measured with respect to some point or the other. The preferred point is O, this is what we said in the previous lectures also. So, you can have VRO, VYO and VBO, that would be the output. What is the value of VRO, VYO, VBO? That would depend on the inverter state. For example, if the R phase top device is on, then VRO is plus VDC by 2. If R phase bottom device is on, then VRO is minus VDC by 2. The same thing about Y phase and B phase. And you totally have 8 different combinations, because this top or bottom can be on, Y top or bottom can be on, B top or bottom can be on. So, 2 multiplied by 2 multiplied by 2. So, there are 8 possibilities, which are called 8 different states of the inverter. And for these 8 different states of the inverter, there are basically the inverter produces 8 sets of output voltages. How many sets of output voltages? 8 sets of output voltages it produces now. So, for these 8 sets of output voltages, we have to find out what are the corresponding voltage vectors. So, these are 3 phase voltages, right. So, these 3 phase voltages we should be able to transform into 2 phase equivalent 2 phase quantities. Let us come to that a little gradually. Let us first look at the load. What is the nature of the load? Let us say the load is a star connected load, but it is a 3 wire load. This R is connected to the midpoint of R phase. This Y is connected to the midpoint of Y phase leg. B is connected to the midpoint of B phase leg. So, R, Y and B are connected to the midpoints of the 3 inverter legs, and this load neutral N is not connected anywhere particularly, it is only R, Y, B are connected. This is a 3 phase 3 wire kind of a load, that is what we are assuming. This is what is true in case of most induction motors. So, you go on with this. Now, the load neutral N and the DC bus midpoint O are different, that is what we need to bear in mind. So, your VRO is the pole voltage. What we mean by the pole? By pole we mean the midpoint of a leg. Why? Because every leg is like a single pole double throw switch, and its midpoint is the pole, and the 2 ends of the legs are the throws. So, we saw that it is a single pole double throw switch, the midpoint is a pole. So, this is the midpoint potential of a leg measured with respect to the midpoint of the DC bus. So, VRO can be plus or minus 0.5 VDC, it depends on whether the top device is on or bottom device is on in the R phase leg. This is what we just discussed a while back. Similarly, VYO can be plus or minus 0.5 VDC depending on whether Y phase top device is on or Y phase bottom device is on. Similarly, B phase also, if the B phase top device is on, it is plus VDC 0.5 VDC, if bottom device is on, it is minus 0.5 VDC. So, these are the 3 possible values of that, and you have 8 sets of 3 phase outputs possible now. Now, what is your space vector transformation? V alpha is equal to 3 by 2 times VRN. This Rn, this is the R phase voltage at the midpoint of the leg, which is the load terminal, but measured with respect to N, the load neutral, and this is not the DC midpoint. This N is different from O. Okay. So, you have VRN plus VYN plus VBN is 0, but your VRO plus VYO plus VBO is not equal to 0. That is an important point you have to bear in mind. You take any of these values here, say 0.5 VDC, 0.5 VDC, 0.5 VDC. What, how do they sum up? They sum up to 1.5 VDC, that is not equal to 0. Similarly, you take any arbitrary values here, here, they will never, almost never sum up to 0, whereas VRN plus VYN plus VBN always sums up to 0. So, now the space vector transformation is V alpha is equal to 3 by 2 times VRN. What is this VRN? You can express this in terms of VRY and VBR. VRN can be taken as 1/3 of VRY minus VBR when you talk of balanced loads. So, your 3 by 2 VRN becomes half of VRY minus VBR. So, once you have this, VRY is VRO minus VYO. Similarly, VBR is VBO minus VRO. So, if you do that, if you plug in those, you get it as half of 2 VRO minus VYO minus VBO. This is your V alpha. So, this is now V alpha. The original space vector transformation is in terms of VRN. Now, we are trying to express that in terms of VRO, VYO, VBO. Now, you see that your V alpha does not depend on VRO alone, it depends on VYO and VBO also. Then, how about V beta? V beta is root 3 by 2 times VYN minus VBN, and VYN minus VBN is same as VYO minus VBO. It is basically the difference between the potential at Y, the midpoint of Y phase leg, and the midpoint of B phase leg. You know, whether the potential is measured with respect to N or O, the difference is the same. So, it is VYO minus VBO. So, here we have V beta, this first part is the space vector transformation. Here the the voltages which are the load phase to neutral voltages have been converted into the pole voltages measured with respect to the DC midpoints. So, now you have V alpha and V beta available in terms of VRO, VYO, VBO. So, that is what you have now. So, for the 8 inverter states, you know the values of VRO, VYO, VBO, you can plug them in to get your V alpha. Again, you know the values of VYO and VBO, you can plug them in to get your V beta values. Thus, for all the 8 inverter states, you can get the corresponding voltage vectors. That is an exercise which we would do. You can actually plug in the numbers and go and play and come things like that now. So, what I would like to do is, I do not want to plug in the values here and show what is what. I can very easily tell you that first consider like something like plus minus minus. So, this is VRO, that what I mean by plus minus minus, this is an inverter state which represents to a situation where the R phase top leg is on and Y phase bottom leg is on and the B phase bottom leg is on. So, there are 3 signs given, they correspond to R, Y and B respectively in that order. Okay. And R is positive, meaning the top device is on, Y is negative, meaning the Y bottom device on, B is negative, meaning B bottom device on. So, VRO is plus VDC by 2 and VYO and VBO are equal to minus VDC by 2. Since VYO and VBO are equal to minus VDC by 2, you can see from the previous slide that V beta is 0. So, it is only V alpha, and you have VRO is equal to VDC by 2, therefore, this becomes VDC. Here it is all minus VDC by 2 and minus VDC by 2. So, it adds to 2 VDC and half of 2 VDC is simply equal to VDC. So, it becomes a vector like this, and this vector has got a magnitude VDC. I have not indicated this here, but I have indicated this in a later slide. So, this inverter state plus minus minus leads to a voltage vector of magnitude VDC at an angle 0, that is V alpha is equal to VDC and V beta is equal to 0 is what it leads to. Similarly, you can do for all the other states one after the other. Now, let us understand this a little better, and then thereby we can see things ourselves. So, what do we see here? We see that when the R phase alone is connected to the positive bus and Y phase and B phase are connected to the negative bus, you produce a voltage vector of magnitude VDC along the R phase axis. Now, everything is symmetric, the machine is symmetric, the inverter is all symmetric now. So, instead of R phase alone connected to positive, you have Y phase alone connected to positive and the other two are negative. See, that is the case here. Here Y phase alone is positive and the other two are connected to negative. So, what you should say by symmetry, you should be able to say now that the resultant voltage vector will be along the Y phase axis, just as it was along the R phase axis, it should be along Y phase axis, and the magnitude of the vector should be same like VDC for this transformation that we are considering here. So, you will get this now. Similarly, you can look at a situation where B phase alone is connected to the positive bus and R and Y are connected to the negative bus. This will produce a vector of magnitude VDC aligned along the B phase axis. So, that is how you can say that. These are easy, you can plug in the values, we had the expressions of V alpha beta in terms of VRO, VOO, VBO, you can plug them in and come up to this now. I am just trying to give a feel for that. Excuse me. Now, if this is your VRO, VOO, VBO, then you invert, you say plus minus minus, you go to minus plus plus, excuse me. Yeah. So, instead of plus minus minus, you have minus plus plus, where all the three are inverted. So, VRO, VYO and VBO are inverted, that naturally means V alpha and V beta should be inverted in sign. It is going to produce a vector along the negative R phase axis. Here the R phase terminal is alone connected to the negative DC bus and Y and B are connected to the positive DC bus, and the resultant vector is along the negative R phase axis. The same arguments are valid for Y phase and B phase. So, you can consider there are 6 possibilities. For each of this possibility, you will have a vector aligned along the positive R phase axis or negative R phase axis or positive Y phase axis or negative Y phase axis and so on, one or the other axis you get. All the vectors are of magnitude VDC. Now, this is accounted for 6, there are 2 other states which are indicated here, minus 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 and plus plus plus. Minus 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 means all the bottom devices are on, that means the load is shorted. Here plus 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 means all the bottom devices are on, the load is shorted. We have discussed this earlier, we know that this is a redundancy that is there in a voltage source inverter. Because of both of this, what happens, the resultant voltage vector is equal to 0. You can say that here all VRO, VYO and VBO are equal, and the line to line voltages VRY, VYB, VBR are all 0. Therefore, the line to neutral voltage VRN, VY and VBN are also 0, V alpha and V beta are 0. These two are called 0 states because there is no transfer of power during these 0 states between the DC bus and the AC side. So, these are called 0 states. The other 6 states are called active states because during this process there is transfer of power between the DC side and the AC side. Whether the power flows in this direction or that direction depends on the operating condition. We will look at that at a later stage, but there is a power flow whenever the active states are applied. Whenever the 0 states are applied, the load is shorted, it is simply freewheeling. The DC bus is opened out and the load circuit is opened out. So, there is no power really transferring between the two now. So, that is what is out. So, there are 8 different inverter states, there are 8 sets of output voltages, 6 sets of output voltages produce 6 voltage vectors of magnitude VDC, we call them as active vectors, and here we can call them as a 0 vector, it produces other 2 states produce a 0 vector now. So, this is what we have, and go here now, you go to the next level. So, what do we have here? 1, 2, 3, 4, 5, 6, I am just reproduce the same thing now. So, I have indicated this magnitude VDC here just for clarity. So, this is our for the space vector transformation that we have defined, you come to this now. Sometimes you should remember that there are slightly different transformations are used, basically they use a scale factor. You can use some scale factor, some root of 2 by 3, certain other factors can be used for some reasons, and this may not be VDC, it may be some k times VDC. So, that depends on the scale factor used, but for the transformation that we defined a while back, these are all going to be VDC now. So, now what is going to happen is this is only to show that there are 8 of them like this, and the next thing is about the reference vector. We will come to this anyway little later. What we do here in space vector based PWM is we use a revolving voltage vector as the reference. What we do in sine triangle PWM, we use 3 phase sinusoidal signals. If you transform 3 phase sinusoidal signals into the space vector domain, it is basically a revolving voltage vector, and therefore, you have a revolving voltage vector here which is shown like this. During some time it will be here, later on it will cross here and go into this, it will go here and it will circulate around all this now. That is what we will do. Okay. So, now let us say you consider a particular instant or an interval, a small interval of time T s during which the vector is here now. Can we produce this vector is the question now. What we did, average pole voltages, recall the concept of average pole voltage. Your pole voltage can be as high as plus VDC by 2 or minus VDC by 2, and therefore, you can produce an average pole voltage anywhere between plus VDC by 2 and minus VDC by 2. The same way, here is the concept of average voltage vector over a subcycle T s now. What you try doing here is, now this is what I have to produce a VRF vector. So, if I apply this active vector 1 for example, for certain interval of time t 1 of the subcycle time T s. So, it is applied for a fraction T 1 upon T s. So, then I am applying this vector which I can call as V 2 vector for some fraction of time T 2 upon T s now, and for the remaining time I am applying the null vector. So, what is going to happen is, I am going to get a vector like this, another component, this is parallel to V 1 vector and it is T 1 by T s times V 1 vector, and this component is parallel to V 2 vector, it is equal to T 2 by T s times V 2 vector. These two are added up to get your V reference vector. This is the average voltage vector now. Thus, you can produce an average voltage vector whose tip can lie anywhere within this triangle. So, you consider that these are two sides of triangle, you join these two tips by another straight line. So, that will give you a triangle. So, you can produce any V reference, any average voltage vector whose tip is anywhere within that. That is what is possible by averaging. So, earlier you are doing an averaging of the pole voltages, two instantaneous values plus VDC by 2 and minus VDC by 2. Here now we are not looking at 3 individual phases, we are looking at them as collectively as 3, all the 3 together as inverter states or the voltage vectors. Now, we use these two voltage vectors and the null vector to produce any average voltage vector within this triangle. That is what is written here now. If you want a vector Vref T s, that Vref into T s, Vref vector into T s will be equal to V 1 vector into T 1 plus V 2 vector into T 2 plus V z vector times T z. So, this is what is called as volt second balance now. This is the reference volt seconds, this is the applied volt seconds. Over a subcycle, reference volt seconds should equal the applied volt seconds, and this is given in an alternate form. This V z vector is a null vector. So, this term is a null vector term. So, you effectively have Vref vector is equal to V 1 times T 1 plus T s plus V 2 vector times T 2 plus T s. That is what is illustrated in the figure now. And what is V 1 vector? V 1 vector is this vector which is VDC angle 0, and what is V 2 vector is the same magnitude VDC, but the angle is 60 degrees now. So, this is what you have as an average voltage vector in a subcycle, that is by applying this vector for T 1, this vector for T 2 and this null vector for T z, you can produce some reference vector like this. That is what we are trying to say, right. So, this is what the volt second balance equation is given here. So, for a particular value of V reference vector, which is basically some Vref and angle alpha, which basically is a magnitude Vref and angle alpha, what should be the values of T 1, T 2, T z? You can just do this. You can decompose them along the alpha axis and beta axis, and you can derive these expressions. What we can call as dwell time. T 1 is the time for which vector V 1 should be applied, T 2 is the time for which vector V 2 should be applied, T z is the time for which the null vector should be applied now. So, this T 1, T 2 and T z, T 1 and T 2 can be calculated like this. They depend upon the magnitude Vref and angle alpha of the reference vector. So, from there you can just derive this, that is from the previous page. You can, for example, these are a vectorial equation, you can decompose it along the alpha axis and beta axis for example, and you can come up with these values for T 1 and T 2. You will get that T 1 is Vref sin 60 minus alpha times T s divided by VDC sin 60. Similarly, you will get T 2 as Vref times sin alpha multiplied by T s divided by VDC into 60 degrees. So, and T z is the remaining part, that is T s minus T 1 minus T 2. For the remaining portion of the time, you apply the null vector T z. So, this is how you calculate the dwell times. We will be doing more on this in the next few lectures. This is just to show that an average voltage vector can be synthesized using these two active vectors and one null vector now. So, what we do in conventional space vector PWM is, we try to apply these vectors now. For example, this is a null vector and this is active vector 1, this is active vector 2, and again this is null vector. How exactly we apply here? We go to the inverter states minus 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 and plus minus minus and so on, and do this here now. If you start here, you can apply this minus 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 to produce null vector, and from here you can switch the R phase and go here, and that would be plus minus minus, and then from there you can switch Y phase and go here to go to plus plus minus, and from there you can switch B phase and go to plus plus plus. So, that is what is shown here. You apply the different vectors, and here you are applying the same vectors in the reverse direction, plus plus plus, all the legs are positive, then here B phase is switched, then Y phase is switched, and finally R phase is switched. You can see that R phase switches like this, Y phase switches like this, and B phase switches like this now. So, what you have is you have 2 active vectors applied in the middle and the 2 0 states are applied at the end. So, the 2 0 states in conventional space vector PWM, what is done is, this is 2 0 states, what is called as T 0 and 7, they are applied for durations T 0 and T 7. T 0 equals T 7 is equal to 0.5 T z, they have to be totally applied for a duration equal to T z. So, you are dividing that equally between the two, that is what is done in what is called as conventional space vector PWM, which I mentioned while earlier that it is the most popular method. We will be discussing this in much greater detail in the following lecture. So, what you are doing is both the 0 states are applied for equal durations of time, that is kind of conventional wisdom. You can apply your null vector using either this option or that option by keeping all the bottom devices are on or keeping all the top devices on. What do I do? Do it both equally, apply this for half the time, apply that for half the time is a simple logic, and you just do this, and that is conventional space vector PWM. As I mentioned, we will discuss more of this later now. So, what you can do is you can apply an average voltage vector like this for some time, and next you can go ahead to the next value. If you have applied this over some Ts now, and over the next interval Ts, excuse me, you can apply another voltage vector like this. Then over the next sub interval subcycle you can apply this now. Here the angles I have shown is 15 degrees, between these two. I am taking my subcycle time to be equivalent to 15 degrees or omega Ts, where omega is the fundamental angular frequency multiplied by Ts. I am taking it as 15 degrees here, which is actually big in many practical inverters of the power level of kilowatts or so. The subcycle duration could be much lower than that, it can be just a few degrees now. It is okay, this is taken for an illustrative purpose now. So, what I am doing is let us say I am applying this average vector for 15 degrees, and after that the next 15 degree interval I am applying this average voltage vector. How I am doing? By applying vector V1, vector V2 and null vector for appropriate durations of time T1, T2 and Tz. The next time I will go here. So, what do I do here? I will apply the same V1, V2 and null vector for different durations of time such that I produce this average. The next subcycle I will apply T1, T2, Tz for another appropriate set of appropriate values, that I produce this average vector. Thus, in every subcycle I produce an average vector like shown here around that now. So, what I am doing is I am going close to a rotating voltage vector. What am I supposed to produce? I am supposed to produce 3 phase sinusoidal voltages, and in space vector domain 3 phase sinusoidal voltage is nothing but a revolving voltage vector. I am supposed to produce a revolving voltage vector. So, that is what I am doing. I am producing a vector like this which stays there, and after a short interval it just moves by a small step, it stays there, after a short interval it moves by that. So, the jump, the step by which it moves is equal to the is equivalent to the interval of time for which it stays there. So, actually what is happening is circular motion is approximated by sampled circular motion, just as sine wave is approximated by a sampled sine wave, and a sampled sine wave is not very different, sampled and held sine wave, that is not very different from an actual sine wave, provided the sampling intervals are close enough. Is similarly these provided these the subcycle durations are substantially smaller than the fundamental cycle, this is a very valid approximation of a revolving voltage vector. That is, you can produce a revolving voltage vector using a 3 phase inverter, and this can be applied to a 3 phase induction machine. So, when you are able to produce a 3 phase voltage vector, it simply means that you are able to produce 3 phase sinusoidal voltages. So, this is about space vector PWM. So, what are we doing? What are the essential differences now? We are using this idea of space vector, and what is a space vector? 3 phase quantities can be transformed into 2 phase quantities. So, now you can see this is only a 2 phase quantity now, and there is a 3 phase sign, and a 3 phase sign becomes a revolving voltage vector of constant magnitude and a uniform angular velocity. So, if it is uniform angular velocity, you sample it at equal intervals of time, you are going to get samples at equal intervals as shown in this particular figure. And so, this is what you go by doing this. So, now what you can do is, now this is how can you produce this. So, circular motion is being approximated by like this, a vector which is stationary here for certain amount of for an interval of time omega Ts. After that it jumps by omega Ts and it stays there for that, and it goes on doing like this now. And how can you produce this vector? For example, this vector can be produced by time averaging of this V1 vector, V2 vector and null vector. And if you are talking about this vector, for example, this can be produced by time averaging of this vector and the null vector. If you are talking about this vector, it can be produced by time averaging of vector V4, vector V5 and null vector. Thus, wherever you are, you can call all this as 6 sectors, and in each sector you use 2 of the neighboring active vectors and the null vector to produce the average voltage vector. I am going to deal with more of space vector based PWM, particularly conventional space vector PWM in the next class. This is only to give an idea of what you could call as the concept of space vector and space vector transformation, and some introduction into space vector based PWM, and a more detailed discussion on that would is reserved for the next class now. Here I have a few references for you, please have a look at this. The first 2 references, one is Holtz et al. That's and the other one by Van der Broek, Skodelny and Stang. These 2 I would call as probably the seminal work in the area of space vector based PWM. So, there were a few works in the mid 80s. These 2 I would say are probably in the second half of 80s. So, these 2 papers reported space vector based PWM. They are early papers in this area of what you would call a space vector PWM. So, for further your knowledge and understanding, you can probably look at these things. And another one is this book, this D.G. Holmes and T.A. Lippo is a book. It covers many things about pulse width modulation and all that. So, it also talks about space vector concept, transformation and space vector based PWM. So, that is a book which can also be used as a reference now. And the last one indicated here is Verma and Narayanan, that is space vector PWM as a modified form of sine triangle PWM for simple analog or digital implementation. So, this is published in IEEE, Institution of Electronic and Telecommunication Engineers Journal of Research. This is a tutorial paper. This is particularly written from the point of view of understanding them easily. So, these are some references I would like to give, and I would give you more and more references as I would go on, relevant references, and I hope that you found this lecture interesting, and we would continue this in the next lecture, and we will discuss conventional space vector based PWM in our next lecture. Thank you very much.